a review of the stuff you've learned in high school chemistry and the 1151 chemistry course. And for today, we're going to go over the different types of bondings, covalent versus ionic bonds, and some coordinate covalent bonds, which you may or may not have heard of. And of course, going over Lewis structures and how the atoms are put together. And so the first thing of any chemistry class is probably going to show you a periodic table. And do I want you to memorize this table? Absolutely not. Right? So what you need to know about the table we'll go over in our next lecture. But there are certain parts of this table I do want you to be very familiar with. Right? And that's not most of the table. If we shrink this down to what we need to know for our organic and biochemistry discussion, it's just this. And so you need to know hydrogen and helium. That's fairly obvious. They're in that top row. Hydrogen has one proton and one electron. Very, very simple atom. Helium is kind of a double hydrogen, where now we have two protons and two electrons. Right? So it's quite different in that there's multiple parts now, but it's not much different than hydrogen in the fact that there's just a simple arrangement. Once we move on past helium, we start building the electrons in multiple different ways. It's not just a cluster of electrons around a nucleus anymore. So we have, in the second row here, lots of other elements I listed there, lithium through neon, but I'm only concerned with the ones on the right here, the boron through fluorine. And the reason for that is we'll talk about a lot of these in organic chemistry. These are the most common elements we're going to see, the ones that I've left on the screen here. So we'll see boron, carbon, nitrogen, oxygen, fluorine. Why are they listed in that order? Well, they're listed from left to right along that row in increasing number of protons. And for every proton I add in the nucleus, I'm also adding an electron around it. So the total charge stays the same, neutral. Okay, so every proton has a positive charge. Every electron I'm adding has a negative charge. And if I add one of each, the total charge remains 0. And so what we do here is a little different when we get to each row of the periodic table. So that's why we're listed in several rows. Every row represents a new orbital that we're introducing, a new valence shell. Okay, so I'm not going to go into too much detail on all the subshells because that's not for this class. You did that back in 1151. But if we look at each row, we need to fill out that row. Every element is trying to fill out its valence shell of electrons. So let's pick one in particular here. Let's look at nitrogen. So right in the center of the cluster over here, nitrogen. Nitrogen is the 7th element in the table. So a few of them are not shown here, of course, but if you count across, it has 7 total protons. That's what that number means. That means it also has 7 total electrons. And it also has a number of neutrons, which don't really get involved in our chemistry. They're involved in nuclear chemistry, but not so much in our normal chemistry, so we'll ignore the neutrons for this course. So it has 7 protons and 7 electrons. But the first 2 of those 7 electrons were in the same lower shell that was occupied by the electrons of hydrogen and helium, right? It's our lowest shells, the first shell. So it contains a maximum of 2 electrons. So if I put those 2 in a lower shell, and then it leaves me 5 electrons to place in the next shell. So the most outer shell, or in this case the second shell, has 5 electrons in it. Right? So that's why it's got 5 valence electrons listed above there. And you notice they're all 2 less than the number they have in total because there were 2 in the first shell. For instance, carbon has 4 valence electrons of its 6 electrons. Fluorine has 7. It has a total of 9 electrons, 2 of which are in the lower shell. Right? And if you move on to higher shells, where you see the silicon through chlorine there, and then selenium and bromine, the shells increase in number greatly, but the most they'll have in their outer shell, except for hydrogen and helium, will be 7 or 8. And we're ignoring the 8s because they have a complete shell. So here we're going to only concern ourselves with the ones that have yet to complete their shell. So anything less than 8, except for hydrogen and helium, which of course can at most have 2. So for example, our nitrogen we were talking about has 5 valence electrons. It would like to get to 8, right? It would like to gain 3 more electrons. But if it gained just 3 more electrons, it would have a -3 charge for 3 more negative things it's acquired. And that's not going to be very stable to gain such a large negative charge, or a large positive charge for that matter. So it'd like to stay neutral if it can, or close to neutral. So instead of just ripping electrons away, the nitrogen would more likely share some electrons with another atom. for instance, if a nitrogen were to share some electrons with a hydrogen. Now, looking at our hydrogen, you probably can guess that it would like to have one more as well to complete its outer shell. Now, remember, 2 is the total that it can have in its outer shell. So hydrogen would like to get one more. Nitrogen would like to have 3 more. So if a hydrogen and a nitrogen were to get together and share their electrons, so the hydrogen donating its 1 and the nitrogen donating 1 of its 7, meaning 1 of its 5 in the outer shell, they would each have an extra 1. Hydrogen would then have its 1 plus 1 it's sharing, so it has 2 in total, and nitrogen would go from 5 to 6. So it's getting closer to 8, but it's not as happy as the hydrogen would be. So in this scenario, you could probably guess that the nitrogen would like to share its electrons with 3 other hydrogens. So that's why we generally have 3 bonds to nitrogen. The same can be said for fluorine, where it's only 1 electron away from filling its shell. So a fluorine would easily bond with, say, another fluorine, or a hydrogen, or a chlorine. Right? So anybody else who needs 1 more would love to share it with somebody else who needs 1 more. Right? So that's how we get a lot of those divalent molecules like H2 and F2 and Cl2. They each want 1 more, so they're sharing one of their outer ones with the other. Okay? If I had to ask you, carbon there with its 6 total electrons, 4 in the valence shell, how many bonds does carbon make? So following that same analysis, how many bonds would carbon make?
4.
4, because it needs 4 more to increase its valence shell to 8, right? It's got 4 in its valence shell now. 2 are down below in a lower shell. We'll ignore those because they're not in the valence shells where all the chemistry takes place. So it needs 4 more electrons, so it's going to share it with 4 other atoms, right? So carbon will make 4 other bonds, right? Oxygen needing 2 more, being at 6, would need 2 more to get to 8, so it makes 2 bonds and so forth. So it's pretty easy to see why this table is very convenient. So carbon would make 4 bonds, nitrogen would make 3, oxygen 2, fluorine 1, right? And if you go across the next row, you may predict that silicon would make 4, phosphorus 3, sulfur 2, chlorine 1. And that's true, but if you go beyond that second row, where you have your carbon, nitrogen, oxygens, and so forth, if you go beyond the second row, it doesn't always strictly follow that policy. So we don't deal with them too much in organic chemistry. We're going to stick to mainly carbon, nitrogen, oxygen for the most part. But if you go beyond that, it is possible to go higher than the number of bonds they normally make. Right? We won't talk about those too much. That's a more advanced chemistry than you need to know. But as far as the ones we're going to talk about, hydrogen making only 1 bond, that's all it can ever do. And boron making 5, boron making 3, carbon making 4, nitrogen 3, oxygen 2, fluorine 1. Right? So why did I say boron 3 and not boron 5? Well, because boron could kind of go either way. It could either share 5 electrons with other atoms to get its valence from 3 all the way to 8, or it could simply give away its 3 valence electrons. Right? Carbon could do the same, but it's very unlikely. Right? But if you're doing that and giving away your electron completely, we're going to call those ionic bonds, right? So I didn't leave those in the table here for you, but if you go back to the other table and look on the left where you have lithium and sodium and potassium in that first column, they have 1 extra valence electron. And I'm not going to ask you to memorize those. But they're more likely, instead of sharing 7 other bonds, they're more likely to just give away their extra one. Okay, so those are going to be ionic type bonds. And the same can be said here for chlorine. Chlorine, instead of trying to make 1 more bond, it can just steal an electron from someone to have its 8th electron. Yes, it will gain a charge, so chlorines become chlorides with a negative charge. And oxygen can do that. It can steal 2 and become oxides with a negative 2 charge, but it's less likely than the ones that only take 1, and so forth. Okay, so what I want you to know from this chart today is the arrangement of these that I've left on the screen, right? You don't have to know the whole periodic table, but I want you to know the arrangement of these few I've left on there, right? Particularly the row with boron, carbon, nitrogen, oxygen, fluorine. Okay. So from that chart, we can have some arrangement of electrons, like I said. The first row with hydrogen and helium has at most 2 electrons in their outer shell. The next row, which is the one I want you to really know, what goes from lithium to neon, can have at most 8 electrons in their outer shell. Well, there's a total of 10 electrons because, as you notice in this little drawing, there are 2 electrons in the inner first shell, followed by a total of 8 in the next shell. So that's up to 10. That's why neon is 10. And in the very next row, when we go sodium through argon, we can again put 8 in the outer shell. Right? So I have 2 in the inner shell, 8 in the middle one, and then up to 8 in the outer one. So it gives you a total of 18 for argon. Right? But if you go one less to chlorine, you're missing one of these in the outer shell. The inners are always full before we fill the outer one. Once we move on to the next row with potassium through krypton, it's not so simple. You notice we've added a whole block in here in orange. Right? It's not so simple as 1, 2, 3, 4, 5, 6, 7, 8. We have this whole block of atoms in here that are not contributing to that outer shell. Right? So when we get to krypton there, it looks like we filled that outer shell, but you notice there's a whole subshell here with way more than 8 in it, right? And that's this middle block. It's called the d orbital, but we're not going to talk about it too much for this course. I want you to be concerned with the number in the outer shell. Right? So anywhere between 1 and 8. Okay, so the difference between covalent and ionic bonds, I have a little cartoon here for you and an explanation of it on the left. It's fairly simple. Let's do ionic bonds first because they're the simplest arrangement here. In an ionic bond, right, like shown here in the middle of the screen, you have 2 atoms, right, and they have electrons in their outer shell, right, some number of them. Let's pretend this one on the left here has a total of 1 electron in its outer shell. So this would be something like sodium or lithium or any of those elements in the first column. And then the other atom here on the right, let's say it has 7 in its outer shell, right? 1 lacking from filling its shell, right? So these two have a common problem. This one has 1 extra electron it would love to get rid of, and this one over here has 7 electrons and it would love to have 8. So they can solve each other's problem simply by giving the electron to the other, as indicated in the cartoon. So this one would not have 1 in its outer shell anymore, and it wouldn't have 0 in the outer shell. The outer shell would then be the next lowest shell, right? So if you look back, let's say you had, sodium, right? So sodium looks just like this neon here, except it has 1 more shell around it with only a single electron. Or you can imagine it looking like this argon. Instead of 8 in the outer shell, it only has 1. If you give away the 1, then its outer shell looks just like neon, and it would be happy. Whereas chlorine, for example, has 7 in its outer shell. It looks just like argon here, but instead of 8, it's got 7 around it. It would love to gather 1 more electron and look like argon. Now, it wouldn't be argon, of course, because you didn't add another proton to the nucleus. All you did was add an electron. So in this case, the thing giving away the electron would then become positively charged, because the number of protons hasn't changed, but it gave away a negative thing. It gave away an electron. So now it has 1 more positive thing than negative things, so it has a positive charge. This would happen to a sodium ion, right? We give away that valence electron and it becomes Na with a positive charge, sodium plus 1. For example, the atom over here that's receiving the electron would now have an extra electron than it had before, but no more protons. So there's 1 more negative thing than positive thing, so it has a negative overall charge. And that would be an example of a chlorine becoming a chloride. Okay? So in that case, our sodium becomes a sodium ion, and our chlorine becomes a negatively charged chloride, and the two of them, since they have opposite charges now, will just associate with each other. There's no true sharing of electrons here. It totally gave its electron away, right? So they just associate with each other now. They kind of stick because they are attracted to one another. This would be like a salt crystal, right? Sodium and chloride attracting to each other. And you can do that many, many, many times, and you'd have your salt crystals. On the other side of the coin for that is, let's say you have 2 atoms here. They're not going to totally give their electrons away, right? They're not that willing to lose or gain them. They're just going to share them. Okay, so in this case, let's say we have 2 hydrogens, right? So this is a hydrogen with its 1 proton and 1 electron, and we have another hydrogen with its 1 proton and 1 electron. Each would like to have 1 more. So if they just share the 2 that they have, right? It's kind of like joint custody of electrons here. So the 2 hydrogens still have 1 proton each, but they're both sharing both electrons. So it's a timeshare, you can think of it that way. The electrons spend some of their time around each of the nuclei. And it's a very simplistic way to look at it, but it helps explain it. So in this case, they don't totally give their electron away, they're sharing both of them. So from each of their points of view, they each have a full shell of electrons, 2 in this case. Or if you did this for fluorine, they would have 7 each, and when they share them, it looks like they each have 8. Okay, so that's a covalent bond. These two atoms aren't attracted to each other now because of the charges like we had in ionic. They're actually bonded together. It's a bond that can't be broken easily. So this is a very strong interaction, right? So this is called a covalent bond because they're sharing their valence electrons, valent, so covalent. These electrons are part of both valence shells simultaneously. That's what covalent means. Okay? So it's a very strong bond. This is what holds most of you together, covalent bonds. But ionic bonds are also fairly strong in that they're attracted to each other because they have opposite charges now. And that's a result of giving an electron away. Okay? So how do we represent that schematically? I don't want you to memorize a bunch of words. This isn't a typical biology class where you memorize a bunch of definitions. So we're going to learn it, and I want you to visualize it, conceptualize it, put it in your head and have a picture, rather than just memorizing a bunch of letters and words on a page. Okay, it's not that type of course. Okay, we do have to learn definitions, of course, but I want you to conceptualize those definitions. So looking at the bottom here, I have a drawing of a nitrogen atom. We're not showing its nucleus, but we're going to say it's a nitrogen. You can say there's definitely 7 protons down in there. And then we have 3 fluorine atoms around it. So each of nitrogen would have a total, if you look at the very bottom, I threw a picture of your periodic table you need to learn. Again, nitrogen has 7 protons there, but 5 of its electrons are in its outer shell. And that's really the number we're concerned with. We're not really concerned with how many protons it has, because it's nitrogen. But it has 5 valence electrons. So I drew those around it. You see the 5 valence electrons here, 1, 2, 3, 4, 5, drawn in its shell. It would love to get that shell to 8. And fluorine has the same problem. It has 7 valence electrons, so it'd love to get its 7 up to 8. So if one nitrogen can share some electrons with 3 separate fluorines, they will all be at 8. And we represent it this way. And the 2 you see between the atoms aren't really belonging to them anymore. The pair I'm looking at here with my mouse, hopefully you guys can see where I'm pointing on the drawing, between the nitrogen and the fluorine on the left, they're each sharing that pair of electrons. So instead of drawing it this way, these electrons aren't necessarily belonging to those elements anymore. They're more like this, where they're sharing them. The other pairs are definitely owned, the ones still in black here, are owned by those atoms, but this pair in green is now shared between these two. So this is a covalent bond. And if you look at it from each atom's point of view now, like this fluorine, there are 8 around it. It's happy, right? It's got 8 in its outer shell. And this nitrogen also has 8 in its outer shell because it's sharing this pair, 3 pairs of 6 electrons here. This one still is owned completely by the nitrogen. And of course the same thing for the other fluorines. They now have 8 in their outer shells. And this is the reason why this nitrogen trifluoride, this NF3, always forms that type of arrangement. Nitrogen rarely only has 2 bonds. It likes to make 3 bonds because it fills its outer shell. If we did the same game with oxygen, it would have 2 things bound to it. So 2 Fs or 2 hydrogens or 2 chlorines. If we did it with carbon, it would have 4 because that's how it would fill its outer shell. So it's pretty easy to see this. And if I take this drawing one step further, instead of drawing all the electrons, I draw the shared pair of electrons just as a line. Right? So every bond you see, these lines we're going to draw structures, represents a shared pair of electrons. It's just a more simplistic way of drawing it than always putting the dots like this. Okay, so we're going to just draw it as a line. But remember, every time you see a line drawn between these elements, it represents a shared pair of electrons. So if I'm counting up the electrons around the nitrogen here, I count this pair up here obviously as 2 because you can see them, but I count this line as 2 as well. So this would be 2, 4, 6, 8 around the nitrogen. Right? Similarly, around the fluorines, you count this bond as 2, and then each pair obviously counts as 2. So 2, 4, 6, 8. Okay, so hopefully that makes sense on how to draw these things. The lines represent a shared pair of electrons. We call those the bonding electrons because they're making a bond between the 2. That's this definition up here. Instead of just memorizing this verbiage up here of a definition, it's the shared pair of electrons, but you can see it visually. It's the 2 they actually have joint custody of, is sharing. It's what holds the 2 atoms together. The other pairs, the ones still in black here, are the non-bonding pairs of electrons. Right? They are involved in chemistry very, very often. We're going to talk about that. But they're not actually making a bond. They're not holding these atoms together. Only the bonding ones are. Okay, so hopefully that visualization puts some picture in your head and not just memorize a bunch of words up here. Okay? So all these bonds we're making and the non-bonding pairs, the lone pairs of electrons here, are going to come into play when we start talking about the geometry of things, which we'll do in our next lecture. Okay. So what about those atoms that have something called double bonds and triple bonds? What does all that mean? So again, this should all be review for you, but let's play this game again with a pair of nitrogen atoms. So here we have 2 nitrogen atoms, each one with its 5 valence electrons. I'm putting the chart on here again to remind you. You'll have this chart, a little simple chart memorized in no time. So nitrogen again has 5 valence electrons. If I put them next to each other, they can share this pair between them, but then that would only put 6 around each one, right? So it'd be 1, 2, 3, 4, 5, 6. So I could do it like that, and they share all 3 of those pairs. Right now we're up to 8 around every nitrogen. Each of these nitrogen atoms is sharing 3 pairs. This one it still owns all to itself, but they're sharing 3 pairs in green. And one way to represent that is like this, with the 3 pairs moved between the nitrogens. Or we said we can represent a pair of electrons by simply drawing a line. So I'll draw this as a triple bond. Right? A double bond would only be 2 pair, and oxygen would want to do that because it needs 2 more. And nitrogen makes 3 bonds to make a triple bond. Right? So it's sharing all 3 pairs there. All 6 electrons are being shared. Right? What if I tried this with carbon? Carbon could make 4 bonds, but you can't make 4 bonds in a quadruple bond. Right? We'll talk about why in just a second. So putting that into practice, looking at the different elements in this row, we say hydrogen can only make 1 bond because it only needs 1 more electron to fill its shell of 2. But all the others, like carbon, nitrogen, oxygen, fluorine, need to make multiple bonds, right? So 2, 3, 4 bonds to fill their shell. So for example, fluorine only makes 1 bond to fill its shell. Oxygen needs to make 2, nitrogen 3, and carbon can make 4. But in the process of making 2, 3, or 4 bonds like this, we could do what we did on the previous slide and say nitrogen makes 3 single bonds. That's totally possible. If I go back and show you that. Nitrogen is making 3 single bonds. Nitrogen can also make a triple bond. It's possible. Oxygen could make a double bond. Nitrogen has the possibility of making a double and a single. That would be a total of 3 bonds as well. So there's multiple ways to do this when you get to larger number of bonds. Carbon, for example, has a vast array of ways it can do this. It could make 4 single bonds. It could make 2 single bonds and a double bond. That still adds up to 4. It could make 2 double bonds. That still adds up to 4. It could make a triple bond and a single bond at the same time. That also adds up to 4. But it can't make something called a quadruple bond. It's just not physically possible. And let's see why that happens. So when we're making these bonds, the first bond between the 2 of them, so between these 2 nitrogens, the first shared pair of electrons is like this little drawing on the bottom right here. So the very center of these bottles represents the nucleus, right? And the clear bottle, or the white bottle here, is represented by representing the first pair of electrons shared. That's shown in the drawing over here. It's a sigma bond, we call it. So the first bond between 2 atoms is called a sigma bond, right, where these orbitals overlap. That's represented by this clear bottle, right? When we make a second bond, it has to be in a different plane, right? Because these are already occupied. So represented by this drawing here, the orbitals are perpendicular to the 2 atoms to each other, and they overlap above and below. That represents by this red pair of soda bottles, right? That would be our second of a double bond. So first one, sigma, it's always the clear one here. Second one perhaps is the red pair here. Right? That's still only a double bond, because this represents 1 bond, 1 shared pair. They're overlapping above and below, but it's only 1 pair of electrons. Then if I make a triple bond, that's a second, what we call pi orbital, represented by the green bottles here. So you can at most have 1, 2, or 3 places where the orbitals can overlap. There isn't a 4th dimension here. We can't have a 4th pair of electrons overlap. There's no physical space for it. So the most you can have is a triple bond. You could have a single, which is made up of only a sigma bond. You could have a double bond, which has a sigma bond and a pi bond. Anything beyond the first is called a pi bond. And we could have a triple bond, which is a sigma bond plus 2 pi bonds, giving a total of 3 bonds. You can't have a third pair of pi bonds because there's no physical space for it, right? So the most you can have is 3 bonds. Right? So let's do some examples of things that don't fit the rules, right? So this is probably the most difficult concept I've seen from students in the past 7-8 years of doing this. This doesn't make sense at first. You may have to look at it a few times. So this is what's called a coordinate covalent bond. It's like a covalent bond. In fact, it is a covalent bond. It's just a different type of covalent bond. I'm sorry, you had a question? Feel free to interrupt. I don't mind. Right? Interrupt and ask your question. So let's do what's called a coordinate covalent bond. All right. First, we have to remind ourselves what a covalent bond is. So if we look back at our nitrogens, for example, and a nitrogen to fluorine example we looked at, what was happening is the nitrogen was donating 1 electron of its valence shell, and the fluorine was donating 1 electron of its valence shell, and they ended up sharing them between them. Okay? Very simple. So if you look at a water molecule, for example, the oxygen in the center is sharing 1 of its electrons with the hydrogen's 1 electron, and that gives them each their complete shell. Oxygen being 8 because it's sharing with 2 hydrogens, and hydrogen sharing with 1 of the oxygen's electrons, completing its shell of 2. And so in every one of those cases, however, the atoms involved in that covalent bond each donated 1 electron. In the case of a coordinate covalent bond here, the difference is one of the atoms did not contribute. Right? So in this bond that's forming between the 2 atoms, it's a covalent bond again, made up of 2 electrons, but it was paid for entirely by one of the atoms. It donated 2 electrons to this bond, and the other donated nothing. Okay? So think of it as a thief, somebody who's sharing and didn't contribute. Or if you 2 people are going to lunch, you don't pay for your own lunch, one person paid for both. Right? You didn't contribute to that bond. And an example here is most often is when an atom needs 2 more electrons to complete its shell. Right? And the most often culprit of that is going to be oxygen. So oxygen has 6 in its outer shell. It needs 2 more to complete its shell. And if I go back real quick and show you a picture. Right? So let's say you have this molecule on the right. If you were an oxygen atom and you had 6 valence electrons and you need 2 more to complete your shell, you don't want to donate any because you're feeling very selfish, and you don't want to, donate an electron to someone else and share one of theirs. You just want to latch on to somebody else's pair that's sitting there. I see lots of options here where I could latch onto this molecule. Right? So any one of these pairs you see in black sitting here looks tasty to an oxygen wanting 2 more electrons. So that's what a coordinate covalent bond is. It's somebody needing 2 more electrons, just latching onto a pair that someone else already owns. Right? And you're sharing it with them. So in the case here, the example I'm using, we have this molecule over here called hypochlorous acid. It's an oxygen, right, bonded to a hydrogen and a chlorine. Right? It's a normal covalent bond here. So oxygen with 6 in its outer shell is sharing 1 of them with the hydrogen who had 1 in its outer shell. So here's my shared pair on the left. I didn't color it differently, but if you look below, it's represented by a bond. Right? So these 2 on the left, electrons, are represented by a bond. Those are being shared between the oxygen and the hydrogen. Each atom, the oxygen and the hydrogen, contributed 1 to that. The hydrogen contributed 1, the oxygen contributed 1 to make this shared pair. On the right, we had the oxygen and the chlorine. Right? Chlorine having 7 in its outer shell contributes 1. Oxygen with 6 contributes 1. There's our bond again. So if you add up the number of electrons around the oxygen, it's up to 8 now. Now it brought, how many of these to the party? It brought 6. So the 4 still drawn as little blue spheres here, right, or circles here. Those 4, 1 of this bond and 1 of that bond, is where the oxygen's original 6 electrons are. In the case of hydrogen, its only electron is now in this bond. In the case of chlorine, it brought 7 to this party, 6 of them are still drawn, and 1 is now in this bond with the oxygen. These are all normal covalent bonds. Everybody contributed. And then we have this hypochlorous acid just sitting here. The chlorine atom here on the right has 3 lone pairs. The oxygen has 2 what we call lone pairs. While the other oxygen floating around here, let's say we have another oxygen floating around in the solution or in the air, and it has 6 valence electrons, shown here in red, just latches onto one of these lone pairs. Right? It says, I'm going to make a bond and share both of your electrons between us. I'm not going to contribute to this. So I'm drawing that as a new bond here. Right? So this helps explain why this is chlorine here, which normally only makes, if you go back to your periodic table, normally it needs to make 1 more bond. It is now making 2 bonds. Right? And I said they can do that if you get to the lower parts of the table. And it explains why chlorine, which normally would make 1, is making 2. However, chlorine still only has 8 around it. The oxygen that latched on didn't contribute to this bond. It just says, I'm going to borrow, with quotes around the word borrow, your 2 electrons with you. I'm going to share them with you. I'm just going to steal them part-time. So that's why we draw a bond here. So this is the coordinate covalent bond. That's what it's called. It's when an atom is making a bond but didn't contribute to that bond. Okay? And there's a simple way to tell when it's doing that, and we'll talk about it later in another lecture. But be aware that it helps explain why sometimes you get atoms like chlorines that making 2 bonds when they should normally make 1. Okay? The same thing's going to happen when we talk about oxygens making 3 bonds instead of the normal 2, or nitrogen making 4 instead of the normal 3. Those are all coordinate covalent bonds, when they make an unusual number of bonds. The most often culprit, or person that's causing that, is going to be an atom that needs 2 more to fill its shell. Oxygen fits the bill. Right? Sulfur also fits the bill. A hydrogen without its electron, called a proton, or H+, also fits the bill. It needs 2 more to fill its shell. Right? Because if it's an H+, it doesn't have an electron. So we'll see that's the case as well. Okay. So any questions on coordinate covalent before I move on? Because I know that's a difficult topic.
Are these common? Is this a common thing, or is this just not that common?
The example I showed here is not so common, right? So chlorous acid and hypochlorous acid here, not so common, but as far as the guilty party being that H+, that is extremely common. That's the basis of protonation and deprotonation. Right, was there another question as well?
I was going to ask, like, the difference hypochlorous acid and chlorous acid is different, just like oxygen.
Yeah, the only difference here between the two is there's an extra oxygen, the one with the red electrons around it, that has decided to show up and talk the chlorine into sharing both of its electrons there. Right? The chlorine really had no say in the matter. Right? So that oxygen just latched on to that pair of chlorines and using it to fill its shell, while at the same time still filling the shell of the chlorine. It's kind of being really selfish there. So this happens often, and this is in fact how we make ozone in the atmosphere. Oxygen normally being O2, you guys are familiar with that. You know it's an oxygen bonded to another oxygen. It's going to have a double bond in between. We'll talk about that when we do Lewis structures in just a minute. But a third oxygen atom just latches on, and that's how we get ozone. Right? And the energy provided to have that happen is from the UV rays from the sun, and it also destroys that interaction using UV rays. And that's why ozone is protective of UV radiation. Okay? So we'll talk about how those arrangements are involved in molecules in just a minute when we do Lewis structures. But any other questions on coordinate covalent? How to detect them? How to decide if it's not coordinate covalent? If we do some examples, you'll probably figure it out.
If it's an element on like the 3rd row or below, is that typically when it's involved then, the coordinate covalent? Is that how we can know?
It could be in that row. It doesn't have to be. You'll see that nitrogen and oxygen can also do this. So it's not exclusive to 3rd row plus, but it happens often in those, like chlorines and bromines and things like that. But oxygen, nitrogen can also do this. Okay, so let's go over the rules of drawing some Lewis structures. It might clear up some questions you have on coordinate covalent as well. Right? So if you remember, I think you guys did this in the previous course. of drawing Lewis structures. And I'll go through the rules again. And I don't want you to memorize the verbiage of the rules. Just tell it to yourself in a short story so you know what order of events to follow. Form an algorithm in your mind of how should I approach the problem. So when you're given a problem and asked to draw its Lewis structure, which are all the things we've been talking about with the electrons, I need to know the total number of valence electrons first. So if whatever element I give you, or molecule I give you, and we'll do an example, whatever one I give you, you need to calculate the total number of valence electrons. And that's easy to do. You just look at each element in the list and add up its number of valence electrons. So if you see a hydrogen, you add 1, because that's how many it has. If you see a carbon, you're going to add a 4. If you see an oxygen, you'll add a 6. So that's why you had to learn that little corner of the periodic table to know how many they bring to this party. So if I see something like water, right? Water is the molecule we'll use as an example as I walk through this. So water has an oxygen, that's 6 valence electrons, and there's a hydrogen there, that's 1, but there's another hydrogen, so that's 1 more, right? So there's a total of 8 valence electrons, 6 plus 1 plus 1. I also have to look at the total charge of the molecule, right? Water has an overall charge of 0, right? There's no charge on that molecule, but sometimes we do have charges, right? So we have to add those in as well. So if you had a molecule with an overall charge of, say, -2, right? Whatever the formula might be, well, I'm not going to use any particular example, but whatever the formula, chemical formula might be, at the very end it says there's a -2 charge. What does that mean? Well, that means there are 2 more valence electrons than we have accounted for, right? Remember, electrons have negative charges, so if the overall charge is -2, and I add up all the contributing valence electrons from the atoms, I add 2 more because it's a -2 charge. If it were a -1 charge, I'd add 1 more. If it were a molecule that had a +1 charge overall, I would subtract an electron because it's missing 1. If you're missing 1, you get a positive charge. Remember, electrons have negative charges. And so we'll add them all up, and then we'll write down the formulas, right? So if we use water, it's H2O, but we don't write it like that. I need to know which electron is bonded, or which atom is bonded to which other atoms. So in the case of water, it's pretty obvious. Hydrogen is never going to be bonded to more than one thing. So it's clear the oxygen's in the middle, and each hydrogen is bound to the oxygen, right? Some of them are fairly obvious like that, but some are not so obvious when I have to tell you which one's in the middle. So if it's not obvious, I will tell you which atom's in the middle. Okay, so we draw it out, and we put single bonds between all the atoms. So if you were to do water, you put the oxygen in the center, you write hydrogen on each side of it. We'll deal with geometries later. It's not so important how you draw them at this point in time. But then I draw a single bond, a line, between them. Remember, that line represents a pair of electrons. Okay? So how many electrons have I used when I draw those bonds? For every bond I write, I'm using 2 electrons. So in the case of water, if you're writing this and drawing it along with me, draw a water molecule, write the oxygen down, put a hydrogen on each side of it, and draw bonds between them. Since I've drawn 2 bonds, 2 lines, a single bond between the oxygen and each of those hydrogens, I've used a total of 2 plus 2 electrons, 4 electrons. How many did I start with? When we added them up in step 1, we said there were 8, right, for this example. I've used 4. So how many are left? 8 minus 4, 4. That leaves me 4 electrons I have to put somewhere. And the first place to put them is on all the terminal atoms, right? The terminal meaning the ends of lines. So that's our hydrogens in this case. They're at the extremities, right? Well, I know the hydrogen can have at most 2, and since I drew that bond, it's already got 2 around it, so I can't put any more. If one of the terminal atoms were, say, a chloride or fluorine or something like that, or a bromine or an oxygen, then I could put more electrons around it until it gets to a total of 8. But in the case of water, the hydrogen at the end can at most have 2, so I'm done with step 3. Then I can add those electrons to central atoms if there's any left. Yes, I have 4 left in my example, so I put those 4 electrons on the central atom of the oxygen. And I must put them in pairs. I don't just place them anywhere. I place them in pairs. As you notice, electrons like to be paired up. So on the oxygen and center, since there are 4 left, I would draw 2 pairs. Where you draw them doesn't matter so much. We'll deal with geometry later. But I have 2 pairs on the oxygen. So your drawing at this point should be an oxygen in the center with a single bond to each hydrogen, and then 2 pairs of electrons drawn on the oxygen. Okay? And then are we finished? Let's check what we do after that. Now we have to check, does each atom have its full set or full octet in the case of non-hydrogens? So does each hydrogen have 2? Yes. Does each other atom have 8? Well, the oxygen has 2 lone pairs and 2 bonds. Each bond counts as 2, so that's a total of 2 plus 2 plus 2 plus 2, giving me 8. Yes, the oxygen has 8. I'm finished. The last thing I should do, if I'm not at 8 for everybody, I should consider making some of the non-bonding pairs, my lone pairs I've drawn, into multiple bonds, double or triple. And we'll do an example of that in just a minute. Okay? And then finally, count up the number of electrons in my drawing and make sure it agrees with my total I started with. Maybe I added some extras or made a mistake somewhere, so it's a check. So if I look at my water molecule I've just finished, I see 2 bonds that I drew, the bonds between the O and the H and the O and the other H, and then I see 2 lone pairs I've drawn, 2 pairs of dots on the oxygen. If I add all those up, I get 8, and the total number we started with was 8, so that's correct. If you don't get those numbers, you've done something wrong, if they don't agree. Okay? And finally, along the way, if I had made a decision on where to put things, was there an alternative decision I could have made? Right? So could I have put those lone pairs on this oxygen or another oxygen or a nitrogen, or is there more than one way to make a double bond? I have to go back and do all possibilities. We do all those possibilities and we call them resonance structures. The more resonance structures you can draw, the more stable the molecule. Some of them may be kind of silly and you go, that's not going to happen, right? You're not going to make 4 bonds to a quadruple bond, so that can't happen. But if it's a reasonable arrangement, then we have to include it in our Lewis structure. Okay, so anytime you come across an ambiguity or a choice and there's more than one option, we draw all of them. Not at the same time, of course, but as separate molecules, as separate drawings. And the more drawings you can come up with, the more stable the molecule. It's an explanation that resonance structures have add to stability. Okay. All right, so before I move on, let's do one more example. I want us to do carbon dioxide. Now, I know you can't see what I'm drawing on my paper in front of me, but you can draw it on your paper in front of you. So I want you to do carbon dioxide. So I would normally draw this on the whiteboard in class, but we're obviously doing this remotely this semester. So to start off, we need to know the chemical formula, and it's CO2. 1 carbon, 2 oxygens. It has no overall charge, right? And I want to draw its Lewis structure. So to start off, let's make the assumption that carbon is in the center. Right, so the carbon atom is in the center of this arrangement, and each oxygen is bonded to the carbon. So the simplest thing you should draw first is put a carbon down on your piece of paper, and like the water molecule we did, draw a bond to each of the oxygens. So a C in the center and an oxygen on each side, and draw a single bond between them. That's our arrangement. Okay, so let's count up the total number of valence electrons. Sorry, go ahead.
Excuse me, Dr. Lee.
Yeah.
We cannot see what you're doing.
I'm not actually drawing on the screen. I'm just talking.
Okay.
So I'm explaining what you should be drawing. That's all I'm doing. So draw a carbon atom. Just write a C on your page. And on each side of the carbon, draw an oxygen. Write an O. That's all I've done. And draw a bond between them. Between the carbon and one of the oxygens, a single bond, a single line, and a carbon and the other oxygen. Okay? So let's count up the total number of valence electrons, going back to our simple periodic table you had to learn. The oxygen brings 6 electrons, right? The other oxygen brings 6 more electrons, and the carbon in the center brings 4. Those are its number of valence electrons. So 6 plus 4 adds up to 16. And there's no overall charge on this thing. CO2 doesn't have a +1 or a -2 or anything like that. It's a 0, no overall charge. So I'm not adding or subtracting. We have 16. In your drawing so far, you have O single bonded to carbon, single bonded to oxygen. That's what you have so far. How many bonds have I drawn? How many lines? I drew 2 lines. Each one represents a pair of electrons. So in those 2 lines, I've used 4 electrons. Our tally was 16. I've used 4. I'm sorry, go ahead.
Is there a way for you to show us how you draw it?
I mean, I can do this, and when we get to in our Discord chat, we can draw things on there and show pictures, yes. But I want to get through this with you drawing it on your own for the first time.
Okay.
We can do many more examples later. So right now you have an OCO. That's all that's on your page. O bonded to C, bonded to O. If I add up the number of valence electrons, I have 16. If you count the number of electrons you've used so far, you've drawn 2 bonds. That's 4. 2 for each bond. 16 minus 4 leaves me 12. That means I need to put 12 more electrons in this thing. We're moving on to step 3 here. I'm adding non-bonding pairs or lone pairs. The first place to put them is on the extremities. That would be on my oxygens. And each oxygen can hold up to 8 total electrons. So I fill up the oxygen's octets. Okay, so if I put 3 pairs on one and 3 pairs on the other, that takes care of all 12 of those remaining electrons. So right now you should have a carbon in the center, single bonded on each side to an oxygen, and then 3 pairs of dots on each of those oxygens. That, if you add all those up, that gives me 16. Right? So there's 3 pairs of dots on each oxygen. That's a total of 6 pairs of dots for 12. And then the 2 lines you drew add up to 2 plus 2 is 4. That gives me 16. I've drawn all my electrons. I'm done. Step 4 says to place any remaining electrons on the central atom, but we have no remaining electrons this time, so we're done drawing electrons. Right? Now let's check and see if everybody has 8. So the oxygen on each side, right, has a total of 8 electrons around it. You drew 6 dots, and there's that 1 bond. That's a total of 8 electrons around the oxygen. Same thing for the other oxygen. But the carbon in the center is not so happy. The carbon in the center has no dots on it, just 2 bonds. So it only has 4 electrons around it. It would love to have 8, but I can't add any more. I've used all my electrons. So what I do now is promote one of the lone pairs into a bond. Okay, this is not coordinate covalent. That's only the case when you're finished. We can judge that. But here we're drawing the Lewis structure. So this isn't making coordinate covalent bonds. This is just following the rules. If I take one of those lone pairs on an oxygen, right? Remember you had 3 on each. If I take one of the lone pairs and erase it and draw a new bond between the carbon and the oxygen, I've kind of promoted those 2 to becoming shared. Now how many electrons will be around each one? Well, the oxygen I didn't touch still has 8. The oxygen I just promoted the electrons from lone pair to bond still has 8. They're still around it. And now the carbon has gone from 4 to 6. Right? I've gained 2 more electrons around it that weren't there before. I'm not quite to 8 yet. I'm almost there. I can see the pattern. I'm getting there. If I do that same thing from the other oxygen, I'll end up with 8 as well. Right? Everybody will have 8. So when you're done, you end up with a carbon in the center that has a double bond to one of the oxygens and a double bond to the other oxygen. Does carbon have its full 8? Yes. It made 4 bonds, as you can see. And each oxygen has its full 8 and made 2 bonds, the double bond. Right? So everybody's happy with 8. But that wasn't the only way to do it. If you go back and look at it, when you were at the step of having carbon with 6 around it, double bonded to one side and single bonded to another, instead of promoting it to a second double bond, I could have made a triple bond on one side. That was also possible. It's less likely, I agree, but it's also possible. So when you have that possibility, I must draw it as a separate resonance structure. And that's what I would do. So I have a possibility of, when I'm done, a carbon in the center, double bonded to each oxygen. That's one possibility, and that's the most likely possibility. And I have another resonance form, where I have carbon in the center, single bonded to one oxygen, and triple bonded to the other. Right? It's not as nice looking. It doesn't fill out the number of valence structures, or it doesn't fill out the number of bonds as equally, but the valence electrons are still correct. They're all with 8. And so we have 2 resonance structures for CO2. But that's what makes CO2 a little more stable than if it only had 1 resonance structure you could draw. Right? And we'll do lots more of these where I actually draw them with you. We'll do them on D2L, or sorry, on Discord, or where I can draw it and show you pictures of it and everything else. We'll do plenty of examples. Right? You can also look on practice tests that I've posted for hundreds of examples of these things. The CO2 being one of them. Right, and then last topic we'll talk about before we move on to geometries and stuff for next time is polyatomic ions. Right, it's just another definition I want you to know. And here we're combining covalent and ionic bonds. Right, so remind ourselves what these things are. A covalent bond is when you have 2 atoms sharing a pair of electrons. Right, We drew the dots between them, and then we drew a line to represent those dots. They're sharing them. I didn't give it to one from the other. They're still sharing them as a pair. That's a covalent bond. An ionic bond was where one atom completely gives away its electron, right? Or one or more electrons. But it gives it away and another atom accepts it. So there's a complete exchange, and they can go their separate ways. The only way they're attracted to each other at this point is if one has a positive and one has a negative charge, and there's just some slight attraction between them. Okay? Here we have a little bit of both. We're going to do that covalent bonding thing, like we'll make a molecule where we have multiple atoms covalently bonded together, and then we'll have that as a group have an ionic bond to something else, right? Another atom or another molecule. Okay? So that's why these things are called polyatomic ions. The word polyatomic simply means there's more than one atom, right? It's not one atom, but more than one, at least two. And that thing as a whole is an ion. An ion means it has a charge. So that polyatomic structure, so a couple of atoms or 3 atoms or 4 atoms, but more than one, as a whole has one or more extra or missing electrons. It has a charge. Right? And then that thing is then bonded to something else through an ionic bond. Right? So here's an example of that below. So I'm going to do potassium sulfate. Okay? The sulfate here, the SO4, is the polyatomic ion. Right? So if you look at the very bottom left of the picture, you notice it's a sulfur, and in this case, sulfur is making 4 bonds. It's unusual, and it can do that. So sulfur is making 4 bonds to oxygens. And those oxygens are each making 1 bond to the sulfur. And if you count up their total number of valence electrons in the structure I've drawn there, everybody has 8 and everybody's happy. But overall, that sulfate, if you add up all those valence electrons and counted them up, and then you count how many valence electrons should come from oxygen and sulfur, each giving 6, and you add them all up, you're going to find that you have 2 extra electrons. Right? So if you add them all up, you'll get 2 more than if you count the number of contributions from their valence shells. So it has a -2 charge. So what we're seeing here is a polyatomic structure. There's 4 oxygens and 1 sulfur, all covalently bonded together, but as a group it has a charge. So that's a polyatomic ion. Right? And then that thing with its -2 charge is just ionically associated. It's making ionic bonds with those potassium ions. Right? Those potassium ions nearby have given up their electron. A potassium, you don't have to memorize the periodic table at this point, but they each have 1 valence electron. They're on the far left of the table. And they would give up 1 electron to become a +1 potassium ion. And so 2 of them have done that, and they've donated them to this sulfate, and that's how it got its -2 charge. But overall, the potassium is not covalently bound to the sulfate. So the structure I've drawn on the right, which is now marked off that you can't see, don't draw it that way. There is no covalent bond between the potassium and any atom of the sulfate. These are ionic bonds, so no lines between them. We don't draw a line because they're not sharing the electron. They gave it away. It belongs to the other molecule now. So a polyatomic ion is simply a group of atoms, 2 or more, covalently bound together, in this case the sulfurs and the oxygens, with overall having a net charge, in this case -2. The potassium on the left is not a polyatomic ion because it's only 1 atom. Each of those potassiums is independent of the other. They're not bound together at all. But if I had something over there that's multiple atoms put together, right, with a charge, it would also be a polyatomic ion, such as an ammonium ion, right? NH4 has a nitrogen and 4 hydrogens around it. The hydrogens are covalently bound to the nitrogen. But overall, that thing would have a +1 charge. That would also be a polyatomic ion. So take a look at these. There's quite a few of them. I know you memorized a lot of groups of atoms in your other classes, sulfates and ammonium ions and chlorides and chlorates and perchlorates and such. But all of those things with more than 1 atom together with a group charge were polyatomic ions. Okay? So next lecture we will go over things like the geometry of how these Lewis structures are put together, how many lone pairs matters, right, and changing the way it moves in 3-dimensional space. We'll also talk about some trends in the periodic table, electronegativity and polarity and size, and things like that, and we'll see some trends in that periodic table. So if you want to leg up on next lecture, look up or Google trends on the periodic table. Okay?